All right, welcome to chapter 13. And this is 13.1. And we are going to be looking at one-way Anova tests. And Anova tests are a way to compare averages between more than two groups. And we've developed a test called analysis of variance, abbreviated Anova. And in this chapter, we're studying the simplest form, just called a one-way Anova test. So we're going to determine if the existence of a statistically significant difference among the group means. So we're going to look at a bunch of data and determine if the averages are far enough apart from each other to determine that they're different. So we use variance to help us determine if the means are equal or not. And we need these five basic assumptions to be true. So each population from which a sample is taken is assumed to be a normal distribution. We need the samples to be randomly selected and independent. Populations are assumed to have equal standard deviations. The factor is a categorical variable, and the response is a numerical variable. So our hypothesis statements will look like this. The null hypothesis is simply that all the group population averages, means, are the same. The alternative is that there's at least one pair of means that are different. We don't know which pair, but it just means one pair is different. So the null hypothesis in symbols looks like this. The averages are all equal to each other. And then the alternative will be at least two groups of the means are not equal. So visually speaking, it would look like this. This example A would be the null hypothesis is true. The averages are close to each other. They're not perfectly equal, but they're close enough. The differences are due to random variation. And here is an example where the null hypothesis would be rejected and the alternative would be happening. So the null hypothesis is not true. All means are not the same. The differences are too large to be due to random variation. So it depends on the sample size. It depends on how spread apart the data is. And it's a complicated calculation that we're just going to use a calculator for. But it's really good to visualize it here. So here's an example. Suppose a group is interested in determining whether teenagers obtain their driver's license at approximately the same age across the country. So you have different parts of the country. We're going to collect four people from each part of the country. So northeast, south, west, central, and east. So it looks pretty similar. East might be a little bit older. Northeast might be young. That's interesting. South and the west. Okay, so it all looks pretty similar, but we will see. And it's really hard to know until you calculate it. So we're going to take these numbers, we're going to put them into our Anova calculator. So here we have our calculator, and I'm going to type in my numbers with a comma in between, and we get our p-value. So this tells us that we have about a 0.017, so about a 2% chance, 1.7% chance of this data actually happening. And that is a very low p-value. So we know low p-values mean we will reject that null hypothesis. So that means there is a difference in the averages. Here we have our averages. Oh, and look at that, group 5, that northeast group, wasn't it? Pretty high. That probably is going to be a big part of it. Here we can see a graph of their averages and their standard deviations. This calculator is nice. It gives you so much information. So there we go. That's it. That's our conclusion. And that's all we can say about these problems. We say that the p-value was lower than 0.05, our alpha level, our level of significance. So since our p-value is less than 0.05, we reject the null hypothesis that all the averages were the same. And therefore, we have enough evidence to say that at least two of the averages are different. We don't know which two, but that's all we can say. So that's an Anova test.